To our presentation. My name is Kevin Lynch. I'm a senior electrical engineering student.
My name is Christopher Reyes, and I'm a senior electrical engineering student.
My name is Angioli, and I'm a senior computer engineering student.
Joseph Murley, electrical engineering student.
Murgimo Greeneye, senior electrical engineer.
Steve Rittman, senior electrical engineer.
Okay, so for our Capstone project, we're designing an energy management system. Now what this basically entails is we hope to create a solar tracking panel that will be connected to a smart controller in which a user can have a better understanding of what their daily power consumption behavior is. And in addition to that, they will also be able to use a renewable energy source that can maximize power input to better accomplish their daily power needs. Okay, so just a software overview. We are implementing a smart controller using machine learning capabilities, and we'll go more into this in later slides, but what this basically means is we want the user to be able to see their daily power usage, and if they're using too much energy during the peak hours when it tends to be more expensive, they can adjust their schedule accordingly. And then from there, we want to implement this onto the hardware portion, which is their solar tracking panel, in order to have a energy management system that can allow the user to save energy and money.
Okay, so for hardware overview, we will be using a solar panels with sun tracking, the maximum power point tracking system with a charge controller to manage our battery, and a inverter which will convert DC to AC voltage in conjunction with a grid tie to inject synchronous AC voltage to the grid. And finally, we will have sensors that will monitor our AC and DC voltage and currents.
So in order to accomplish this in a timely manner, we realize it's not practical for all of us to attack one portion of the project at once together, because we do have to finish this by May. So what we decided to do was to split up our team into a hardware portion and a software portion. And what we're going to do is we're going to work simultaneously with one another. While some of us develop the software portion, it will go hand in hand with the hardware that they're developing. And once we reach certain milestones, we'll implement them together and then continue on from there to reach the next milestone. We feel that this is the best way to go about it to make sure that we do have a final working product in May.
Alright, so as we find different ways to improve energy efficiency, our main focus today is going to be on solar energy. And as a result, recent studies show that our main source of energy comes from 67% of fossil fuel, 20% of nuclear, and only 7% of renewables. Our design will be mainly to maximize power being outputted through the solar panels and reduce energy costs.
So for hardware design requirements, as I mentioned, we will be developing a sun-seeker tracking system for our solar panel, which will be accomplished by using a dual-axis solar panel tracking system. Moreover, in order to maximize the power output from our solar panel, we will be using a maximum power point tracking system in conjunction with a charge controller. The purpose of this maximum power point tracking with the charge controller would be to do the impedance matching for the solar panel and at the same time safely charge our battery system. Finally, we will have a power inverter system with the grid tie. The purpose of the power inverter system with the grid tie is to convert the DC voltage into AC voltage, and where the grid tie system will actually synchronize this AC voltage with our grid so that we can accomplish injecting power onto the grid or to the load.
For the software portion of the project, we need to create a system that can quickly respond to changes in the system. We plan on using sensors placed throughout the system to monitor it. We need to also be able to predict power usage by the user, who should also be able to configure it easily in things such as setting their schedule. We also need to keep track of data on the long term for prediction.
Okay, so for high-level design, our DC source voltage over here would be our solar panel system with the maximum power point tracking system, which will be basically to either charge the battery, or we can actually bypass the battery charging system by managing the switch where it says 3-level switch. So basically the power produced from the solar panel could either charge the battery or it can be directly supplied to the inverter. The inverter will then be responsible to convert this DC voltage into AC voltage. The inverter, in conjunction with the grid tie, will be responsible to producing a sinusoidal output voltage with minimum total harmonic distortion, which will be accomplished by using a filter. So the step-up transformer is basically needed to step up our output AC voltage to a required 120 RMS voltage for our system. So finally, the main controller for our system can either will operate on these switches. The purpose of that is either we can inject the power directly to the grid, or we can actually bypass the grid, isolate our system from the grid, and just support the load directly. The green ovals that you see in the picture, they depict our AC current and voltage sensors. And on the other hand, over there, the gray ovals represent our DC current and voltage sensors.
Okay. So in order for us to extract the maximum power out of our solar panels, we decided to use a dual axis tracking. Dual axis tracking provides 2 degrees of freedom as opposed to a single degree of freedom on a single axis tracking, or no degree of freedom on a flat panel. In order for us to realize this, we're using 2 linear actuators here. As you can see, the front view and the side view. This front view here depicts the movement of the linear actuator and when the sun is moving east to west every day. And then on the side view here, we'll have the second actuator that will adjust for the angle throughout the seasons from summer to winter. We chose this design in terms of a gear-driven system as opposed to a gear-driven system because it has less gear mechanics involved, and we decided that this would be more feasible for us to do in a timely manner and give us more time to focus on other portions of the design.
Okay, so the Raspberry Pi, as said before, will track the power generation and usage using the sensors placed throughout the system. These usage statistics that we track hourly will be saved into a MySQL database that the user can, using a separate application, the user can look at this data on a graph so they can track their yearly power usage. We will communicate with Arduino units throughout our system through the Raspberry Pi's GPIO pins, and the user will be able to configure the system using an easy-to-use graphical user interface.
So in order to achieve accurate sun tracking, we'll be using our Arduino Do as our microcontroller. It will be responsible for 2-axis control. It will receive information from the solar tracking system. We will mount 4 photodiodes onto the solar panel. These will produce voltages depending on how much sunlight is hitting them. 2 voltages from the photodiodes will be sent to a differentiator where it will subtract the voltage. This voltage will be sent to the Arduino Due, where it will try to make a balance of 0 volts across the 2 photodiodes by adjusting the 2 motors within the 2 linear actuators that we're using in our dual axis control. Additionally, we'll be using external real-time clock to determine the best time for the solar panel to go back to the starting position for the new day. We estimate this will be around 7 to 8 p.m. usually on average.
Additionally, we'll use a second Arduino Do for implementing inverter control. The inverter control needs to accomplish 3 things, which will be external voltage control, internal control for the current, as well as phase lock loop, PLL. During this time, we were able to download MATLAB support packages for Arduino and to test certain situations where we can attempt to apply this to our design. Essentially, we're going to use the 10-bit DAC or 12-bit, depending on the accuracy of our signal. We want to input the current and voltages from the sensors into our DAC, and we want to output PWM signals from our Arduino for the gating pulses for our inverter. The grid tie, which is a central portion of this design, is very imperative since it takes your DC voltage from your renewable source and makes it an ideal source to be put onto the grid. In order to do that, we will need a power conditioning system, as Asip said here, that will include the inverter, the line filters, and the step-up transformer. The Arduino, as it stated in the previous design, previous slide, will take care of the inversion control. This equation here at the bottom is for the power that's controlled on the grid. It is the product of the voltage of the inverter with the voltage of the grid divided by the connecting impedance between the inverter and the grid, and this is the angle between the grid voltage and the inverter voltage. By adjusting this angle, we can effectively control the power that goes onto the grid, and this is very important in order for us design to implement our renewable source onto the grid.
So this picture over here depicts an H-bridge type of inverter. So we will basically be using a 3-level inverter. The purpose we chose a 3-level inverter is because with a 3-level inverter we can achieve 3 stages of voltage, which would be positive to 0 voltage, 0 voltage, accomplishing that, we will be actually able to minimize the total current through our inverter. So this will help us minimize the losses through our inversion state. So as Mergim said it before, the Arduino, one of the Arduino DUIs will be used, will be our controller for our grid tie and for our inverter system. So Arduino DUI will be producing pulse width modulation based off of what's the phase angle and what type of frequency do we want from the inverter. So based off of that, we will be operating these four NMOS transistors over here. So that will help us accomplish a DC to AC voltage output. Right over here we have a very crude second order LC filter, which will be used to filter out all the harmonic distortion and convert our modulated DC voltage into a sine wave. So additionally, basically, we will be using a NMOS RRF 740 as our NMOS transistors for our H-bridge. The reason we chose that is because this transistor is capable of handling up to 200 DC volts and 10 amperes of current. In order for us to drive our circuit, the modulation which is created by the Arduino DUI does not have high enough voltage for us to drive our NMOS transistor. So for that purpose, we will be using a driver circuit, which is IRF2110. In this simulation, I didn't incorporate the driver circuit because it's not as easy as to achieve it in simulation. So instead, I used the 2 gain amplifiers, which actually just accomplished the crude version of the MOSFET driver circuit.
Since we'll be charging and discharging quite a large battery, we'll need a smart charge controller to keep the battery safe and efficient. Within this charge controller will be a temperature monitoring system to keep the battery safe from extreme temperatures such as 60 degrees Celsius and 0 degrees Celsius, where the battery should be disconnected from charging to cause no harm to it. In addition, we'll be able to apply a safe charge current to the battery when it's at a low voltage. Applying a larger current to the battery at this time can cause severe overheating, which can damage the battery. But once it gets to a safer voltage, we'll be able to apply the fast charge current to get the battery to its rated voltage at the fastest possible time. Since we'll be dealing with a higher voltage system, the solar panels voltage will have to be converted down to a safer voltage for the battery, and this will keep the battery healthy and maintenance-free for a long time. More specifically, we'll be using an MPPT charge controller, as mentioned previously. This stands for Maximum Power Point Tracking. It just makes sure that we can maximize the power extraction from the solar panel to the battery. And the way this is done is that the power from the solar panel and the voltage of the battery currently is frequently it's compared. So it will determine the best possible power output by doing this comparison. It will convert this maximum power to a DC voltage that will produce the most efficient current to the battery. The way this is done is through a DC to DC step-down converter. It's a closed-loop feedback where the duty cycle within the converter is adjusted so that we get the correct voltage. And this is most effective during colder seasons. Those that might not know, the solar panel actually produces more power during the colder season, so we want to take advantage of this.
Alright, so some of the risks we'll be facing as 2 separate teams, which will be on the software side. We'll need to learn how to implement machine learning into our system. And on the hardware side, we'll need to learn how to implement grid tie. We need to have a deep understanding of power systems and follow certain standards that impact these with our system. Another risk we'll need to help prevent is helping prevent system failing. And then we need to accurately control power flow from the inverter to the grid, and we need to monitor our budget costs. So to reduce risk, our first step was to minimize the functionality of our GUI and not make it as complex as possible. And we'll need to be able to model our system onto MATLAB Simulink and then implement it onto Arduino. And then we'll need to buy sensors that will be able to monitor the voltage and current. With this, the sensor will need to have high precision and high frequency. And our sensors will also need to be able to detect system failure. And we'll also be working with some faculty members, and we'll use some of their equipment, such as our Arduino board and the Raspberry Pi that the department has supplied for us.
So as you can see here, The most expensive products in our project will be the solar panel, the lithium-ion rechargeable battery, and the high current sensors. Luckily, the software portion of the project will not cost anything, but we do come up with a total of about $530 worst case scenario for the hardware. With the $250 budget that the college supplies to us, this comes out to $280 that we can split 6 ways, and that's roughly about $50 per person. But again, this is the worst case scenario, and we expect to actually bring down the prices of some of these products.
Okay, so with the schedule, again, we have it split up between the software team and the hardware team. The software team will begin by first working with the sensors and figuring out how to integrate the sensors and work with them with the Raspberry Pi. After which we will team up with the hardware team and implement that into their system. After which we will begin working with the GUI and the database for the user to use. That'll take about 3 weeks, and if things are going well, we'll be able to begin working with machine learning in our project.
Essentially for the hardware, the 2 portions of the hardware design which will take most of the time will be the grid tie inverter, as well as the dual axis control system. We will most likely need to spend time during the break to come in and start working on the phase lock loop implementation on the Arduino for the inverter. And for the testing stages, we will be using test equipment from our sustainable lab in order to see if we're getting the proper output of our panels into our inverter.
Okay, so due to the nature of our project, there are several standards we have to take into account, and after consulting with Dr. Mayako, we found that the New York State energy standards are going to be the ones that are most important to follow. And the reason for this is that we need to make sure that as we're injecting power back into the grid, we match the frequency. We have about a plus or minus 3 hertz error on a 60 hertz wave that we're injecting back into the grid, so we need to make sure we take that into account. And in addition to this, we'd also have to consult with the utility companies when installing this into a house, because there are certain standards that they maintain, so we have to make sure that it's not going to do any damage to the product or to the grid when we're injecting it back on.
In addition to this, we'd have to adhere to the JADA battery standards, which basically just means that we're keeping our batteries safe from extreme temperatures. So if it reaches extreme temperatures such as 60 degrees Celsius or 0 degrees Celsius, we would have to disconnect the battery from the system to make sure that the battery isn't causing fires or explosions, any damage.
Okay, so in summary, we're basically developing a solar tracking panel that the user can have more of an idea how much energy they're being supplied from this, and then they can also better understand their behavior. It's important to note that in modern day society, we know that our current form of energy consumption is not sustainable for the long term. So it's important that as much research can go into solar energy and understanding how it can work, so that we can continue to thrive and prosper from an energy standpoint. We'd also like to thank Dr. Horine for his help, and we've already consulted Dr. Amin and Dr. Mayako, and I'm sure that we will continue to consult them as time goes on. So thank you.
Okay, so we're a little bit behind, but as you can see, this is a large group with large projects, so we can take a couple of questions and hopefully make it up. Go for it.